Hi, welcome to Chem 6161. These are the exercises from the chair transition state. We will start with exercise number 1, that basically is the reduction of this ketone using this triacetate boron hydride. Okay, remember the first step will be the coordination of this hydroxyl group with the boron, and what we will get is this compound. Okay? Then we can wonder if this oxygen will coordinate with the boron, but this boron has a negative charge. That means that will not be possible. What will happen is that we will have the protonation of this ketone to make it more active, and then the hydrogen will attack the carbonyl group. Okay? If we take a look in this transition, in this attack, we will discover that this is a 6-member transition state that we can draw as a chair transition state. I will draw the 2 chairs. Okay, this is one, and this was the other, and I am more comfortable working with the boron in this position. But you can put it in the position that you want. This will not change the end of the experiment. But for me, it's more comfortable to put it like this. Okay, this is the boron. If this is the boron, number 5, then I will put all the other substituents. Here has to be the hydrogen. Here is the carbonyl that is attacked by the hydrogen. I will not draw a carbonyl now, and I will only enumerate this 1, this has to be 2, this has to be 3, 4, this is a 6. And I will do the same here. This is the hydrogen, this is attacked to the carbonyl, and then this is 5, 6, 1, 2, 3. Then in carbon number 2, what I have is this group. That means that okay, sorry, if the TBS is going up, in this case, what we will have is the TBS in this position. Sorry. CH2 TBS. Okay? And if this is up, here we will have the, okay, the hydrogen and the hydrogen. Okay, these are the 2 structures, the 2 conformers of the 6-membered transition state in his chair conformation. Which chair is more stable? This is the next question that we have to answer. Okay, this chair presents this substituent in axial, while these chairs present this substituent in equatorial. Obviously, this chair will be more stable than not this one. Okay? This will be the most stable chair, the most stable conformer. That means that we will follow with this conformer. We delete this, and now I will put the carbonyl group. Okay, the carbonyl group can be up. Okay, and then the phenyl is coming like this, or could be the opposite. I draw again. O could be going down, and then the phenyl is going up. Now we analyze these two transition states. In this case, the phenyl more or less occupy an equatorial position, while in this case, the phenyl more or less occupy an axial position. That means this transition state will be more stable than not this transition state. For this reason, we take this transition state. Okay? And now the only that we need to do is to draw the attack. Okay, this is after the attack, and we put this in zigzag. That if we put this in zigzag, what we will get is this final configuration. This will be the major diastereomer of this reaction. Okay? As a summary, what I did is basically I check the transition state, that is a 6-member ring. I draw the conformers, the two chairs transition state for this reaction. Okay, and I choose the transition state that presents a chair with this substituent, the substituent number 2 in equatorial position. And then I check which orientation of the carbonyl group will be more favored, that in this case is this, and I get the final configuration. Okay? Good. We will do exercise number 2. In exercise number 2, what we have is this cyclohexanone, and we add LDA, and next we add metallite. Okay? Well, how we start this reaction? Basically, we react the cyclohexanone with LDA, we will form the enolate. Okay? And now this is a 6-member ring. I can draw the conformer, the most stable conformer. I put my eye here, okay, to see in this direction, and I numerate. Always it's useful to numerate 1, 2, 3, 4, 5, 6. I draw the double bond. Okay, if I draw the double bond, that means that here, going in front of us will be the O lithium, okay? This is carbon 1, this is carbon 2, this is carbon 6, and this is carbon 3. Okay? I draw both because I will need to draw the two possible conformations. And then I draw the rest of the half chair transition state. I can go up or down. Here I will put it up. This is carbon number 4. Then okay, this will be 1, and the other, if I go up here, I will go down here to draw the other possible okay, 4, 5. And now only that I need is to locate this terbutyl in the position. If this terbutyl is up, okay, the terbutyl in this case will be here, here will be the hydrogen, in this case the terbutyl will be here, and here will be the hydrogen. Which of these two conformations will be more stable? Obviously, here we have the terbutyl in an equatorial position, here we have the terbutyl in an axial position. That means that this will be more stable. Okay, I delete this compound. Now, what reaction we are doing? We are doing the enolate addition to a methyl iodide. Okay, this is an enolate. That means that we will not consider any Burger-Zunitz trajectory. An enolate is the orbital pz that is here. That means that will take place up or down the attack. And remember that because it's an enolate that is attacking an alkyl halide, this alkyl halide is receiving the reaction that is doing is a SN2. Okay? If you remember, the SN2 is with inversion of configuration. That means that the approach has to be like this in both cases. Okay? Then we analyze which trajectory will be better. Here, the hydrogens doesn't have any problem to come to the enolate. However, here this is crashing with this substituent, means that this approach will be disfavored. Okay? That means if the approach is up, what I will have is I will have this compound, okay, that if I draw it in the right way, I will have this as a major compound. Okay? That means I make the enolate, I try to find which is the more stable conformer, and then I do the approach of the nucleophile. Remember that this has to be perpendicular, okay, because we are doing a nucleophilic attack, and I check which trajectory will be the less hindered, taking in account that we have a SN2 transition state. Okay? Good. Then we go for the last exercise. That basically is the opening of an epoxide. Okay, in this case we have this cyclohexane epoxide, and we treat with sodium hydroxide, and then obviously the hydroxide will open the epoxide. Okay? The question is, where will attack the epoxide? Where will attack the hydroxyl group? In this part of the epoxide or in this part of the epoxide? Well, what we can do is, first, as usual, I recommend to numerate the structure, and then I will draw the half-chair transition state. I put my eye here, okay? Where is epoxide? And then I do like, if this was a double bond, this has to be 1, this has to be 2, this has to be 6, this has to be 3. And then, as I did before, I can do both. Okay, I can draw the half transition state up, this, or I can do it down. Okay? And then I check which will be the most stable. Six, 5. Okay, in the position 4 I have a metal. If the metal is up in this position, I will have the metal here, hydrogen here. While here, I will have metal here and hydrogen here. Which will be more stable? Where the metal is in equatorial position, that is this. Okay, in this conformer, the metal is in an axial position. That means that should not be possible. Well, that should not be possible. Should be more unstable and